Today's problem is find H index difficulty medium. You are given an array, citations, where each element, citations at I, represents the number of citations received by the ith paper of a researcher. You have to calculate the researcher's H index. The H index is the maximum value H such that the researcher has published at least H papers, and all those papers have citation value greater than or equal to H. Maybe an example would help here. So for this input, the output is 3. Why? Because there are 3 papers, or there are at least 3 papers having citations greater than or equal to 3. 3, 3, and 5. What about this one? Output for this one is 2. Now it says there are 3 papers that have 2 or more citations, but the H index can't be 3 because there aren't 3 papers with 3 or more citations. There are 3 papers with 2 or more citations, but that that doesn't count. It has to be the same number. So there are 2 papers with 2 or more citations, and then if you get a bunch of zeros, your output is going to be 0. Size of the citations array is between 1 and 10 to the 6th, 1 million. So we don't have to think about the possibility of an empty array. We don't have to think about the possibility of non-negative numbers being in there. That wouldn't make sense, would it? Citations is between 0 and 10 to the 6th. Expected complexities. O of n. Auxiliary space, also O of n. Okay. Topic tags. That's interesting. Sorting. Binary search. Well, the input is not sorted. If we sorted it, normally the complexity would go to n log n. There are sorts we can do that are O of n, like a bucket sort. It's not usually we do bucket sorts on inputs with a smaller range, not 1 to a million. Oh, wait a minute, is that right? Yeah, 0 to a million. Binary search. Okay, so let's say we did a bucket sort. That's O of n. But then binary search, a lot of those buckets are probably going to have zeros in them. So we need another pass over the buckets to remove the buckets with zeros, right? So I'm not sure if a binary search is going to help us, because actually with a second pass over the array, we could find the answer, I think. So let's look at what we could do here. We can create so n is the citation's length. We can well, let's see. So n is the citation's length, and then we create an array of citation counts from, of size n plus 1. Why is it n plus 1? Well, because a paper can have up to n citations. A paper could even have more than n citations, although those would all go into the n bucket. Because we need, well, I mean, it wouldn't make sense to have more buckets than the length of the, well, it wouldn't make sense to count citations beyond the length of the original array. In other words, if you have an array with 5 elements and you have an integer array, buckets, you have 6 buckets, so you can count 0 to 5. That's fine. You don't need to count 6 because the author hasn't published 6 papers. So you're not going to have 6 papers with a citation of at least 6. So the buckets, the count of the array is n plus 1. We're going to populate the frequency array. We'll go through the citations. For citations greater than or equal to n, they're counted in n. So again, if in this case, if there was a paper that had 6 citations, we would still count it as 5. Else, citation counts citation. Otherwise, we just put it in the appropriate bucket. Okay. We are going to iterate from the highest possible H index. So we're going to start with n. We're going to go down towards 0. And if we find, we're also going to keep track of paper count. Initially, it's initialized to 0. But as we go through the array, we are going to keep track of the paper counts by adding the citation counts. Now, once the paper count becomes greater than or equal to H, because we're doing this, starting with the highest number, once we find an H where the paper count is greater than or equal to H, then we can just return H. How would that work for these examples? Well, let's see. So if we did a bucket sort for this first one and then started with H equal to n, what is n? 5. So paper count, well, we have one paper with a 5, so the paper count goes to 1. Is 1 greater than or equal to 5? It isn't. We go to 4, there are no 4s. We go to 3, there are 2 3s, so now our paper count is 2 plus 1, that's 3. Is that greater than or equal to 3? Yes. So there's 3 papers with citation counts of at least 3. Okay, let's try this one. We'll start at 5. There's one 5. So paper count goes to 1. Is 1 greater than or equal to 5? No. We go to 4. Paper count becomes 2. Is 2 greater than or equal to 4? No. We go to 3. There is no 3. We go to 2. Paper count then becomes 3. Is 3 greater than or equal to 2? Yes. So we return 2. So that should work. And then let's say one thing about this, return 0. We really should never get there. We're guaranteed that there will be at least one paper, but we need to return a value for every path, or Java won't compile this for us. So let's do a compile and run. Let's do a sanity check on this. Okay, that worked. And then go ahead and run it. All right, good. What did we learn there? I guess that if you get something where you're pretty obviously going to need to sort you're pretty obviously going to need to sort something to get the answer, and they tell you we're expecting a runtime of O of n it might be a good time to start thinking about how could I do this with a bucket sort. So go ahead and like the video, subscribe to the channel, and I'll send you free of charge problems of the day in your inbox every weekday. Okay, we'll see you next time.